What is soil anyway? And for those of you who have not taken a course in soils, we need at least a 2-semester course to define and begin to understand soils. And here's just a limited number of the books that I acquired when I was an undergraduate and a graduate on urban soils, or on soils in general. I would like us to think of soil as being the least renewable physical component of the ecosystem. And there's an old adage that's been around for a long time that says it takes about 1,000 years to form an inch of soil over top of parent material. So if you remember the slide that Stu showed us, where we have maybe 4 or 5 feet of original soil left on top of the compacted soil, you can imagine that even though we're no longer on a rock parent material, it would take many years to establish or reestablish soil functioning. I want to mention just briefly Hans Jenny, who many think of as being the father of modern soil science. And in 1941, he published a book called Factors of Soil Formation. Jenny was a professor at UC Berkeley, by the way. And Hans is known for the so-called cropped equation. Soil is a function of climate, organisms, relief, parent material, and time. And this is a functional factorial model for understanding soil formation, modification, and management. And I would say it's also a way of understanding what things we can change and have control over in urban soils. One of the things that Jenny says in his book is it's problematic whether any definition of soil could be formulated to which everyone would agree. Fortunately, there is no urgent need for universal agreement. We can agree or disagree with that at the moment, but for the time being, I'd like to say we need to be able to look at these different factors if we want to understand how soil is functioning in an urban environment. So which of these variables can we control in designing urban green infrastructure? I'm not going to give you an answer to that. I'm going to ask you to think about that, please. Here's an idealized soil profile of a natural soil. You'll notice that at the top we have organic matter, slightly decomposed, moderately decomposed, highly decomposed. We then have an A horizon, mineral mixed with humus and dark colored. We then have an E horizon. So this is where we get material that is leaching out of the higher horizons. And then a B and C horizon that are accumulating these things that have been leached out. And then finally, at a fairly great depth in many instances, bedrock. C horizon here, very little weathering actually occurring. So this is an idealized soil profile. Here we're looking at two different soils. We have here on the left of your screen, this is a greenbelt soil, this is an urban soil. On the right, we have an agricultural soil here. And this is a soil that has been heavily disturbed because of plowing. And you might remember Stu mentioning compacted plow layers here. Well, this here, the top 8 to 10 inches of soil in the profile on the left have been disturbed repeatedly, like on an annual or semi-annual basis by plowing. Look at what's going on the left here. We have, I'll call this parent material, the material from which soils are developed. At the bottom of this left slide, this left profile, we have the first dump, literally imported and dumped parent material brought in from who knows where to bring the soil up to a desired grade. We then have a second dump on top of that. And then on top of that, a third dump. And then in the top 8 to 10 inches, we have a drainage layer dump that has larger rock components in it. And then finally, a thin veneer of topsoil. This is a very different kind of situation than we might expect to see, even in a highly disturbed agricultural kind of setting. This is the front of the Soil Survey Handbook for Tompkins County in New York, where I live. And here is a soils map adjacent to Ithaca, New York. Look at this mosaic of soils. We've got this complex mosaic that reflects the interaction of all of the different variables that are affecting soil development, including things like where it occurs in the landscape. Look at this. Here, within the Ithaca city limits, we don't have anything. There is no soil mapping. Now, recently Los Angeles has had the foresight to start categorizing and mapping some of the soils within the urban area, and that's a good thing. That's a very innovative sign of progress here. But historically, that's not what soil surveys actually looked at. Soil surveys historically omitted urban areas because the emphasis was really on agriculture. And even on the front of the Tompkins County Soil Survey, you see this contour plowing with alternating bands of cover crop and plowed land. This is New York City, a satellite image of New York City. And here you can see Central Park here in the middle of Manhattan Island. Welcome to the Anthropocene, everyone. Where is the soil or green infrastructure in the 5 boroughs of New York City? And does soil even exist in this gray, impervious landscape? Here's some soil profiles underneath pavement. Look at this stuff here. You've got different areas, probably some of this stuff, all of this has been compacted, right? Some of it has been imported and then compacted. Some of it, like look at the blue area here in the top right photo. That bluish gray suggests that we have an anaerobic environment. So the biological components of this soil, the biological functions, are being severely restricted if they exist at all. So how can we expect to grow anything in this much less a tree? So here is, I will propose a partial answer. We should use structural soil. And what I'm going to be talking about primarily is Cornell soil. This is a patented mix that's been patented to Amarak, and it's been patented because it's kind of difficult to mix and get right. Here is an example from an interpretive sign on the Cornell campus showing Cornell structural soil. And what it's doing, the intent, is to increase the volume of soil that is available to trees and plants that are beneath or near paved areas. But essentially, it's supposed to support pavement. Now, that's not something that soil under natural conditions typically would do. Here's an example, a close-up here. We've got these stone, this is washed crusher-run stone. We've got soil particles, and we also have these interstitial areas that would either hold air or water. Here are the ingredients in the CU soil. Washed, angular, crushed stone lattice. And angular here. We need something where you've got point supports for overlying weight. Within this stone lattice, you introduce 20% clay loam. That's got to be imported from someplace else. 2 to 5% organic matter. That has to be imported too. And then gelscape tackifier, which is an artificial product. It is something that will aid in uniform mixing and help the clay loam and organic matter stick to the stone lattice. So this is not something that you necessarily want to do or should feel able to do in your backyard. Here are just a couple examples of rooting systems. On the right here, this is a tree that was grown in a compacted urban soil. Both of these tree systems were planted at the same time. On the left, this is growing in a structural soil. So you've got much more root mass development, both in terms of depth and horizontal distribution in the structural soil. But this structural soil is the component of a much more complex and designed system. And depending on which of these kinds of examples you might look at in the literature, up to 48 inches of structural soil is deposited underneath a pavement. And this isn't just normal pavement in many instances, like normal asphalt that we see here in the lower portion of the screen. We have pervious pavement or pervious asphalt, which is very porous, but it requires routine maintenance and vacuuming in order to keep it from being plugged. So this is a pretty complex system. Okay, how can we start to think about things that we know about green infrastructure? Here's an example, a caricature or cartoon showing a native forest with the soil underneath it on the left. We've got many inputs, processes occurring within the soil, as well as outputs, both subterranean as well as back to the atmosphere. Here's an urban planting, and this is from a book about urban structural soils. Where are the inputs and the outputs? We haven't even begun to quantify these. Okay, so we really need there's room for lots of research on the performance of urban soils in general and structural soils specifically. This is going to be accomplished through long-term monitoring. And when I say long-term monitoring, we're probably looking at the decadal scale here, as mentioned by Stu. We want to monitor tree performance and health. We want to monitor changes in the soil itself, in the structural soil, and the functions that it's performing. And ultimately, we want to look at the ecosystem functions and services provided in the context of this so-called green infrastructure. And then we can't really forget global change. This is the new normal, and we need to manage for radical changes in our ecosystems. And those of you that are living in California have recently experienced some fairly major rainfall events and runoff events, and I saw on the news last night cars literally getting stranded in flooded roadways, albeit in San Francisco. Look at the graph. This is showing monthly precipitation. This is in the upper left-hand corner. This is Los Angeles, the red line here. This is Ithaca on the top here. For basically May through October, there is essentially no water often deposited in Los Angeles. If we look at the pictures on the right, the top picture here, this is Ithaca's water supply. On the bottom right, this is Lake Mead. This is Los Angeles's water supply. So I pose the question here, what is the water footprint of urban green infrastructure? We've got radical differences across the space of the United States here in terms of the annual distribution and amount of rainfall. The demonstration projects that LA is doing right now provide an ideal modified situation in which we can monitor and understand the way urban green infrastructure is actually funding. Now, is actually performing, is what I should say. How are we going to fund this? I'm suggesting that we need to partner with cities. Los Angeles can catalyze this, with cities across the United States, and get funding for a research coordination network. This can be obtained through the National Science Foundation, USDA, USGS, and on the right here are two current examples that have shown up in the journal Science or EOS just in the past month. There is a large nationwide native soil observation project that is just being initiated. And then there is an agricultural project that has been around for a few years now. We really need to have something like this for cities as well. And I propose that we might want to borrow from Yenny here. And perhaps we could title this project a functional factorial models for soils in green infrastructure projects. And I want to end by saying, this is just outside of my office here. I live in a tunnel. There's green and obviously infrastructural functionality at the end of the tunnel. So, thanks very much for your attention.